Thank you for joining our WMG Steel Group Colloquium. Today, I have a great privilege to introduce our speaker, Professor Dmitry G. Eskin from BCAST, Brunel University, UK. So, Dmitry received his engineering and PhD degrees from Moscow Institute of Steel and Alloys, Technical University, Russia, in 1985 and 88, respectively. After that, he worked as a senior scientist in the Baikov Institute of Metallurgy, also as a senior scientist and a fellow in the Materials Innovation Institute, Netherlands. And he also worked as an associate professor in Delft University of Technology from 2008 to 2011, where he conducted fundamental and applied research on solidification processing of metallic materials and alloy development, with major contributions to mechanisms of hot tearing, macrosegregation, grain refinement upon direct chill casting. In 2011, Dmitry joined Brunel University London, UK as a professor in solidification research. His current research concerns fundamentals and application of ultrasonic cavitation to melt processing as well as alloy development. He is a well-known specialist in physical metallurgy and solidification processing of light alloys, co-authored of more than 350 scientific papers, 7 monographs, and a number of patents. Among his books are Multicomponent Phase Diagrams, Applications for Commercial Aluminum Alloys, Physical Metallurgy of Direct Chill Casting of Aluminum Alloys, Ultrasonic Treatment of Light Alloy Melts. Professor Eskin is also a former chair of TMS Aluminum Committee, former editor of Journal of Alloys and Compounds, currently member of the editorial board of Ultrasonics Sonochemistry. He also received various light metals Cast Shop awards from TMS and other prestigious institutes. Thank you, Dmitry, for taking time to give this talk to us, and floor is yours.
Yeah, thank you very much for a very kind introduction. I'm really great, I think, judging from your words. So can you see my screen, yeah?
Yeah, please.
So I can start, okay, great. Just give me a second, yeah. So, thank you for attending this seminar. So I will be talking about ultrasonic melt processing, and I'm sorry I will be talking mostly about aluminium rather than steel, because for steel it's quite challenging to do ultrasonic melt processing. First of all, I would like to acknowledge a lot of my former and current collaborators, my PhD students, postdocs, and people in other universities with whom I collaborate over the years. You see, it's quite multinational team, although mostly we were placed either in Netherlands or in Great Britain. So I will start with a little bit of history on the subject. Then we'll introduce you to some basics of cavitation and how we can study it, and what are the mechanisms of this cavitation in different processes. Then we'll talk about these applications of ultrasonic processing to degassing of melts, structure refinement, and other applications like dispersion, exfoliation, and atomization. So ultrasonic processing is a historic subject, so studied for quite some time, but in the last 20-30 years there was an increasing interest to this technology because it offers some sustainable, eco-friendly means of achieving the goals which are typically achieved through additions or through introduction of some gases. So it's gives you an eco-friendly way of tackling industrial problems. In the heart of the ultrasonic processing is cavitation. So cavitation is, by definition, is creating of cavities. And when we talk about liquids, is a creation of cavities in the liquid. So when the static pressure on the liquid reduces below liquid vapor pressure, so small vapor-filled cavities are formed in the liquid. So there are two major types of cavitation in liquids. One is hydrodynamic cavitation, which is famously known for damaging impellers of ships. And that's usually when the water or liquid comes across this solid liquid interface with a very high speed, and at some critical speed there is a disruption, so that the water cannot flow over the interface anymore, so it starts to disrupt this interface, creating bubbles. This hydrodynamic cavitation is used also in useful applications, for example, in atomizers, emulsifiers, and some mixers. Acoustic cavitation, which we mostly deal with, is a result of alternating pressure created in liquid by passing the high-frequency acoustic wave through the medium. And then, because it's alternating pressure, so wave has ups and downs, so it's at some point pressure exceeds the threshold and the liquid disrupts, creating bubbles. And this is also its uses in emulsification, medical uses, cleaning. You all know about ultrasonic baths, and materials processing. So this is, as I said, a scientific field with a very rich history. So the works, fundamental works and practical works on ultrasonic cavitation and its applications date back to 1930s, 1920s even. Notably, in already 1954, there was a literature review published on the applications of ultrasonic processing to metals. And in 1981, another review was published by John Campbell on application of vibrations to melt processing. My father worked a lot in this field, and he published his first monograph on this area as applicable to aluminium in 1965, and since then a number of other monographs were published. So it's a historically very rich area. So what we can expect when we talk about ultrasonic cavitation? You have a vibrating source here, which vibrates in this direction, high frequency, usually above 17 kilohertz, and then when it reaches certain power, cavitation starts. And cavitation is concentrated near the tip of the source, but it produces bubbles and a lot of mesoscopic, microscopic flows. So you can see that it creates mixing, it creates vigorous movement of liquid, and it creates special phenomena in the cavitation area itself. So, and you can see it produces noise, high frequency noise. If we talk about specific areas, so we talk about usually cavitation area region, which is directly underneath the source of cavitation of vibrations. It's usually roughly the size of diameter of the probe or sonotrode, sometimes a little bit larger than that. And then there are downwards flow which recirculates like that. So this is experimental observations. These are PIV measurements, particle image velocimetry measurements of the velocities. And velocities in this area of the secondary flows is in range of centimeters per second, centimeters per second. While here, the processes are very quick, but also very high speed. So actually, when you talk about the implosion of a single bubble, so each cavitation bubble, and that I didn't mention this. So when cavitation bubble is created, so it also pulsates in the acoustic field. And because it has certain resonance size, after a few cycles of pulsating, it collapses, it implodes. And when it implodes, it creates in the center huge pressure, which also results in a huge increase, but very short in time, but huge increase in the temperature. And the velocity of this implosion is around 1.5 kilometers per second. So this happens on the scale of single bubble. But in the bulk volume, the velocities are much slower, velocities of the flow. So what happens actually when we talk about ultrasonic processing? There are a lot of phenomena which are interesting and relevant to processing itself. So first of all, we have cavitation and acoustic streaming, which was illustrated in the previous slide. And we can observe it in transparent liquids, now in intransparent liquids, in synchrotron, and we can do modeling. Then we have cavitation zone, which can also nowadays we can observe it. And we can also measure acoustic pressure in the cavitation zone and outside cavitation zone, measure the attenuation, because of course cavitation pressure is maximum close to the source of vibrations, but then it attenuates through the volume. Then there are phenomena which are associated with this cavitation. First of all is degassing. So liquid usually degasses. So when these bubbles are formed, they're filled with gases which are dissolved in the liquid. So, and then by that, a liquid can be degassed of the dissolved gases, for example, oxygen in water or hydrogen in aluminium, and that we can measure and observe in transparent liquids. Then it activates, cavitation activates inclusions, which is creating better wetting conditions on the surface of inclusions present in the melt, for example, oxides. There is a sonocapillary effect, so under conditions of cavitation, liquid can penetrate in much smaller openings, for example, crevices at the surface or small openings in the filter. So much smaller capillaries, and that's called sonocapillary effect. So cavitation helps to overcome capillary pressure. Wetting I already mentioned. So also under conditions of cavitation, the nucleation of melts on inclusions is enhanced. Also, the solid particles can be fragmented, deagglomerated, and exfoliated in the liquid under conditions of cavitation. In liquids, so immiscible liquids like oil and water, for example, can emulsify very efficiently under conditions of cavitation, and you can also have atomization of liquid when it drops onto this vibrating surface. So these all phenomena and mechanisms which we use in materials processing using cavitation. So cavitation looks differently in different liquids. So depending on the properties of the liquid, cavitation can look differently. With big bubbles, with no well-defined cavitation zone and flows, like we saw in water or liquid aluminium, you have very well-defined cavitation zone and flows. Very slow processes in the high viscous liquids. So we can not only observe the cavitation in different liquids, but also can measure acoustic pressures using cavitometers. So it's a special device which transforms mechanical vibrations of the probe into electrical signal, and then this electrical signal can be converted using fast Fourier transformation into the spectrum. So and then also calibrate it to the real pressures. So we can do it in water. We could, for a long time, do it in low temperature liquids like water since 1950s. But nowadays we can also do it in liquid aluminium using metallic probes. So this is an example of such measurement showing that you can you have attenuation of pressure in liquids. So moving from the tip of the probe or sonotrode to the side, you will have attenuation of the pressure. But also you can see that it's not necessarily that 100% power, so maximum amplitude of vibrations is better than smaller amplitude of vibrations. And that's because you have not only attenuation of acoustic waves in the liquid, but also have shielding of acoustic waves from the melt or from the liquid by the cavitation zone. You can imagine that cavitation zone is a zone where you have a lot of bubbles. So you have not a continuum liquid medium anymore, so you have a bubbly liquid. And bubbly liquid attenuates very quickly, or let's say absorbs very quickly energy, acoustic energy in itself. So which means that if you have very well developed cavitation zone, there are a lot of things happening inside, but not much going outside this cavitation zone. All energy is consumed within. And that's what we don't want. We want to treat a larger volume of melt or liquid. So we want to have enough cavitation, but not too much cavitation. And that's a very important practical conclusion from these measurements. So we learned from these acoustic pressure measurements, which I think we pioneered like 8 years ago here in Brunel, so that we may have a very strong shielding effect if the cavitation zone is very well developed. We have also, we know now how this shielding and also attenuation happens in liquid real melts, and we know that the acoustic streaming, so this secondary flows, acoustic flows, are affected by acoustic power, and we can also draw a lot of practical solutions which we can apply in our practical applications of liquid metal processing from these measurements. We can also do synchrotron studies of how cavitation happens in liquid metals nowadays. So this is example of acoustic flows in liquid aluminium, and this is cavitation zone here. You can see bubbles formed, and this example showing bubbles, cavitation bubbles, and how the implosion helped to fill a small channel here, which is, we think, is a first ever evidence of sonocapillary effect observed in liquid metals. So we have now reached means to study cavitation processes. Sorry, what I did, I press end. It's not end yet. Let me go back. I'm very sorry, so I pressed wrong button. So I will just need to go. Oops, what happens? Yeah. When cavitation bubbles collapse, or the cloud of bubbles collapse, they produce shock waves. And nowadays we can also visualize the shock waves. You can see this appearing, this semicircles, which are actually pressure shock waves emitted by a collapse of bubbles or cloud of bubbles. And we can also measure acoustic characteristics of the shock waves, and they are believed to be responsible for a lot of mechanical effects induced by cavitation processing of liquids. So from these observations, in situ observations, we learned a lot. We've confirmed some concepts which we knew before, like sonocapillary effect, but we also observed for the first time shock waves in liquid metals or liquid, generally in liquids. We can also see how the cavitation helps in or let's say how cavitation interacts with solid particles floating in the liquid, and what we can expect from this interaction. One of the major applications of ultrasonic melt processing, if as applicable to liquid metals and specifically to aluminium, is nucleation. So we want to refine the structure of liquid metal, or sorry, of solid metal, by assisting nucleation of solid phases during solidification. And of course, it starts from nucleation. The more nucleons you have, the finer the structure. So there are a number of hypotheses and theories how cavitation can assist nucleation. One is very fundamental, is cavitation-assisted homogeneous nucleation. So when bubble, as I said so before, when cavitation bubble collapses, it actually produces a lot of pressure inside, and this pressure creates undercooling. So increased pressure upon bubble collapse increases the melting point of aluminium by about 60 kelvins, which means that effectively, if you look at the ambient temperature of the melt is locally undercooled by about 60 degrees, which a lot. So that's going to create homogeneous nucleation sites. On the other hand, oscillating bubble surface before collapse also produces some undercooling, and that's relatively small undercooling, about 1 K. So in a fundamental work by Hunt and Jackson in 1966, it was suggested and shown experimentally that this effect, so collapse of bubble and increasing of melting point, local melting point, is a leading mechanism of homogeneous nucleation. But in liquid metals, homogeneous nucleation almost never happens. So you cannot use this explanation for explaining grain refinement in real melts. So here we talk about heterogeneous nucleation, and heterogeneous nucleation happens on the substrates which are present in the melt. Typically, if we talk about aluminium, but also steel is the same, is oxides, carbides, borides with the sizes of a few microns. So what cavitation does, it first of all cleans the surface of these particles from whatever contamination is there, and also what is very important, from absorbed gas on the surface, so allowing the access of the liquid metal to the surface of these particles. And then it also promotes wetting and filling of small surface defects via sonocapillary effect. And so these wet particles, especially if they have good crystallographic match with aluminium, become active, and they can serve as a substrate for solid phase to be formed. On top of this, cavitation fragments into metallics and dendrites, and by that creates new grains, new substrates or new grains, and that also assists in grain refinement. So activation of substrates is very difficult, of course, to observe and prove experimentally, but what we can indirectly we can say that very frequently, if we treat our melt above the liquidus in relatively wide temperature range, and then solidify material, we frequently find oxide inclusions inside intermetallics, which indirectly shows that these intermetallics were nucleated on these oxides. We also have very interesting evidence from synchrotron studies where we see that intermetallics of aluminium to copper are nucleated on oxides on aluminium oxide after this melt was processed with ultrasound. So this is a direct evidence of nucleation on oxides. And if there will be no cavitation treatment before, these oxides will be inert, they will be not wetted by liquid aluminium, and so there will be no nucleation. Fragmentation is another powerful means of grain multiplication, grain refinement. It works always, but it only works when you do it below liquidus, because you need to, in order to fragment something, you need to have this. So if you talk about fragmentation of aluminium dendrites, for example, or intermetallics, you need to do it in the area in the temperature range where this solid phase already exists. And it works very well. So we had a lot of in situ observations how cavitation can fragment intermetallics. You can see here and here. So basically by crushing it, the only interesting thing that it is not happening instantaneously. So actually, it's a kind of fatigue mechanism, high frequency fatigue mechanism. So this is an example of aluminum copper alloy in synchrotron. So without ultrasonic processing, you can see that there are huge elongated needle-like intermetallics formed. When you do ultrasonic processing, ultrasonic sources here, so the flows detach some of these intermetallics and brings them back into the cavitation zone. So we don't see cavitation zone in this frame, but they're going to cavitation zone here. And then when you switch off ultrasound, that's what you have. These are fragmented intermetallics sediment and create much finer structure. And that's what happens also in real alloys when we process them with a liquid, with ultrasonic cavitation. So we learned a lot from this in situ observations. Some of these observations are quite unique to date, but we learned a lot, and we continue to work in this area. And it's very scientifically rich area of research. Another thing is deagglomeration. So if you have agglomerates of particles, like you have, for example, when you add particles into liquid aluminium to make a composite material. So they tend to agglomerate. And then what cavitation does, this cavitation bubbles, this agglomerates of particles, cavitation basically scrubs the surface, cavitation bubbles scrubs the surface of these agglomerates and deagglomerates them. So instead of having big chunks of agglomerates, you have individual small particles released into the liquid. So what is important that because it's a gradual process, it takes a long period of time. So if you want to make nanocomposites by adding nanoparticles into aluminum melt, you need to allow some time, 10, 15, 20 minutes for the process to happen. If you try to do it in 10, 15 seconds, you will not be able to achieve the result because of the mechanisms of deagglomeration. We also have emulsification assisted by cavitation. Here, example of oil in water, and you can see that this is cavitation zone here, spreading. It's very high-speed observations, and here the emulsions start to form. Here, emulsions start to form. We also looked at the positive effect of dissolved gases. Which will enhance cavitation, also by that enhance emulsification. So another very interesting recent application of ultrasonic cavitation is exfoliation, for example, making graphene. And we had a good project on that, and we observed and achieved very efficient exfoliation of graphene in eco-friendly solutions like water, or water ethanol solution, which makes this graphene suitable for biomedical applications. And yet another application is atomization, and that may be interesting for people who work in additive manufacturing, because ultrasonic atomization is one of the means to produce good quality powders for additive manufacturing. And here you can see how this, so this is a vibrating plate. And here you can see how droplets or layers of liquid metal, or of liquid, sorry, in this liquid, atomizes when it touches the vibrating surface. And there are mechanisms associated with that. We published and are currently publishing papers on this, which is quite, again, scientifically rich area. Let's now talk about applications. So we talked about mechanisms, some fundamental mechanisms. What are the applications of ultrasonic processing? Again, it is there is a history behind this. So we know that there were examples of industrial scale applications in the 20th century, 1965 degassing, 1970s, 80s application to large scale direct chill casting, producing billets and ingots from aluminum alloys. These works are continue now in China, for example. This example were very similar experiments in DC casting in China. We work more on fundamentals of this, or let's say, technological development of this processing, so smaller scale, but we do this research in BCAS here, also during DC casting. So what the applications of ultrasonic processing to processing liquid melts? Degassing, filtration, structure refinement, deagglomeration, dispersion, especially for making composite materials, but also for improving the efficiency of added grain refiners, and exfoliation to make 2D materials. Let's talk about degassing. Degassing was one of the first applications of ultrasonic processing, dating back to mid-1920s for the degassing of liquid glass. Of course, in glass, degassing is important because you don't want to have glass with bubbles. But in application to liquid aluminium, it probably dates back to 1960s and still is a developing area with new equipment available. So the idea is that you create cavitation bubbles. They're filled during their pulsation. They're filled with dissolved gases. Then they grow, absorbing more and more of dissolved gas, and then they float and release the gas into atmosphere. So this is degassing. It's very, very efficient. You can see here that you can efficiently, in a few minutes, degas from 0.3 cubic centimeters of hydrogen per 100 grams of aluminium to below 0.1. There are also processes of partial so the stages are this partial degassing, or it's really deep cavitation degassing, and depending on the level of gas which you achieve in liquid metal, you can have either stable degassing effects, so that you can degas, and this liquid metal can stay there for minutes or probably even hours before casting, and you will have this lower level of hydrogen. But if you want really to have very pure melt with almost no hydrogen or very low concentration of hydrogen, and you achieve very deep degassing, you need to be aware that you need to use the melt right away. Otherwise, it will regas and absorb hydrogen from the atmosphere. Just to tell you that hydrogen comes into liquid aluminium from moisture. So humidity in water, in air, so water and air, H2O, reacts with aluminium to produce aluminium oxide, which remains on the surface of the melt, and hydrogen, which is dissolved in aluminium. And aluminium can dissolve, liquid aluminium can dissolve a lot of hydrogen. But solubility of hydrogen is very low in solid aluminium. So during solidification, if you don't extract hydrogen, you will have porosity, which you don't want, of course. So practical applications of implementations of degassing. So this example of European project, which we had a few years ago. So ultrasonic degassing of roughly half ton of aluminium in foundry. So this is also, I showed this example. This is degassing back in 1960s in foundries. So you can see the difference here in multiple sonotrodes. Here we use one sonotrode, but it's moving, which is a technological advance. This is example of degasser from company Southwire, United States. They use combined cavitation with nitrogen or argon flow. So it's not purely ultrasonic degassing, but more carrier gas degassing enhanced by cavitation. Another major application, which is very important and attracted a lot of interest, is structural grain refinement. So you can go from relatively large grains in solid metal to very fine grains. And I mean, you can see here that this is a very historically rich area. So you can see here dates back to 1930s, and a lot of works were done in 1950s, 60s, 70s, 80s, and are still going on and go on. So the mechanisms are cavitation-assisted heterogeneous nucleation through activation of substrates, and also fragmentation of solid phase. But note that there are specific temperatures range for these mechanisms. So for that, you need to treat above the liquidus. For this, you need to treat below the liquidus. So you can achieve the refinement of primary phases, primary intermetallics. This is an example of aluminum silicon hypereutectic alloys, piston alloys, usually 12 to 18% of silicon. So very efficient refinement of primary silicon. Also primary intermetallics of other origins, aluminum 3 titanium, aluminum 3 zirconium, aluminum 3 iron, can be efficiently refined. And by refining intermetallics in hypereutectic aluminum alloys, you can achieve structure which allows these alloys to be used. Because, of course, alloys with such intermetallics cannot be used if the ductility is almost zero, fracture toughness is very low. But if you refine these intermetallics, you can actually start to use these alloys. So when we talk about grain refinement, so this was a refinement of primary intermetallics or primary phases. If we talk about grain refinement, we talk about primary grains of base materials, so aluminum or magnesium. And here we want to activate substrates, multiply nucleation points, and you can actually achieve non-dendritic structure if you have excess of solidification sites. What we suggested a few years ago, and we use it, you can combine these two. So you can refine primary intermetallics by activation of substrates and refine them to such size that these intermetallics start to be nuclei for aluminum. This particular example is aluminum 3 zirconium phase, which we refine from this coarse intermetallics to this very fine intermetallic, which then by its size and chemical or structural properties serves as a very good nuclei for aluminum, and you can achieve very good grain refinement by this kind of two-stage mechanism. Fragmentation of primary dendrites works always. If you do ultrasonic processing during solidification, it always works, but the problem is that you're very limited in volume, because if you go to the semi-solid material, so the volume which you can treat is very small, because of course you have a lot of solid material around, so there is a lot of attenuation of the acoustic waves, so you're confined to a very small volume, so practically it's seldom can be used. There are a lot of schemes of practical implementation of ultrasonic processing in shape casting and direct chill casting. So these examples of direct chill casting for aluminum alloys with multiple sources of ultrasound in large molds. We work a lot on this in terms of technology development, and I mean, here there were basic principles known and the results were achieved. Now we know much better about what happens inside via modeling. We know that how cavitation how ultrasonic processing changes the shape of the sump of the billet, changes the distribution of alloying elements, of how flows are arranged and so on, and that help us to optimize the processes. And also, as you saw in previous slides, and here we use mostly, and most of the people when they study this or try to use it, they use treatment in the mold. This is DC casting mold. So you use your source of ultrasound is embedded into the mold, which means that if you have numerous molds, which is currently the practice when you cast extrusion billets, you can have 28, 64 molds on one table, so you need to put ultrasonic source in each of them, which is of course practically is not viable. So if we can move the treatment to the flow, to the trough from which melt comes into the molds, we can scale up the process. And these are the results of this of trials where we did processing in the trough, in the launder, and we achieved quite good grain refinement by this processing. So there is a way, in our view, it's a way of upscaling this process to to commercial industrial applications. When we talk about deagglomeration dispersion, it's mostly about most interest, let's say, is making composite materials. Although this ultrasonic dispersion is widely used in other areas, food, chemical, pharmaceutical industries. But if when we talk about metallic alloys, we talk about mostly composite materials and also master alloys or immiscible alloys. So these examples of dispersion of insoluble particles. If you just do mechanical steering, this is TiB2, titanium boride particles in aluminium. So just mechanical steering gives you a lot of agglomerates. If you do ultrasonic processing, you have much better dispersion of these particles. If you do both ultrasonic processing and mechanical steering, you have quite good distribution of particles which are deagglomerated and even distributed in the matrix. With nanoparticles, it's more difficult because their specific surface is huge. They really want to stick together, but even there, with longest processing time, you can achieve deagglomeration of particles and even embed them into the matrix. In exfoliation, I mentioned graphene. So we developed a technology of making eco-friendly graphene purely by cavitation. So if you don't know, currently graphene by liquid phase exfoliation is produced using chemical exfoliation. So you add very poisonous and harsh chemicals to water or to other solutions, and then these chemicals, they spread the crystal structure of graphite, so kind of puffing it up, and then you use mechanical mixing or ultrasound to separate the layers of graphene. Here we don't use any chemicals, and the exfoliation happens naturally only by cavitation. And the last slide is about atomization. So we have currently a project on additive manufacturing where powders are produced not by us, but by our partner, by ultrasonic atomization, and the quality of particles is very good. And the results of additive manufacturing using these particles is also quite impressive. But we're in the middle of the project. I cannot tell too much about that, so because not everything is, not much is published yet. So to conclude, ultrasonic processing, in my view, has great potential in industrial applications. And the key for successful scaling up of applications is flow management. So how you treat larger volume with less sources of ultrasound, and that can be only organized through clever flow management. So how flow goes, how melt goes around. The mechanisms, currently we have means to study mechanisms, experimental means and modeling. I didn't touch about modeling, but there's a rich literature on modeling of these processes, which are developing. It's very difficult to model correctly this process because multi-scale and multi-physics, but it's started to emerge. We also, we're quite, because it's quite active in ultrasonic processing. We have a few projects in last years, and we consider ourselves as a quite internationally leading group in this area. So, and then this is the final slide, which you accidentally saw before. There are a few books which you can refer to if you want to learn more about that. Thank you very much.
Thank you, Dmitry, for nice talk. Any questions from audience?
What is it that stops you from applying this to steel? I appreciate that the temperatures are very high, but I seem to recall from a long time ago that people have been applying ultrasound during welding of steel. So what is it that is actually stopping you from doing something for iron?
Yeah, thank you. It's not a difficult question. It's a very clear question, and I have a clear answer to that. So that there are two aspects here. one aspect. If we try to use what we use in the liquid aluminium, so direct introduction of ultrasounds using the sonotrod, inserted into the liquid melt. So unfortunately, we don't have materials which can be stable in liquid steel at these temperatures, and then transmit acoustic wave. So there is no way to directly introduce ultrasound in steel, in liquid steel, or for this matter, other high temperature materials like titanium or nickel and so on. So that's the straightforward answer. But you can do it indirectly. Indirectly, there are two ways of doing this indirectly. One is not efficient, in my view, but people tried it, to introduce it through the mold. So you have, if you cast, for example, continuous casting of steel, and you have mold, you can vibrate the walls of the mold, and through that transmit vibrations into the liquid metal, so indirectly. But this is a very inefficient way because you have huge losses of acoustic energy going through a tool, through the mold, and then to the melt. So you have air gaps, and then you have interfaces. Each of them will reflect acoustic power back. So it is very inefficient. And in small volumes, people demonstrated it's possible, but I don't think that it's possible on large scale. There is emerging way of introducing ultrasonic vibrations into the melt, but indirectly by high frequency electromagnetic vibrations. And this is a technology which was developed, I would say, at least patented and developed on the level of modeling and some concept trials by University of Greenwich, group of Professor Pericleos, Koulis Pericleos, and they suggested that you can use high frequency or superimposition of two high frequency electromagnetic fields to induce resonance in a volume of liquid metal. So in the center of the volume, you will have cavitation conditions. And that may work. And then, of course, because it's indirect, so you don't have anything immersed into the liquid metal, it can be applied to any material, any conducting material. Yeah.
Yeah. So supposing that we are not interested in cavitation, but in fragmentation, okay? Does the problem
but you need to have cavitation in order to have fragmentation. So fragmentation
doesn't it just involve shaking the material?
Yeah. I like it, shake it. Yeah. So you can shake it, of course. Yeah.
It's very weak at those temperatures.
Harry, this is a different area. This is called vibration processing. So if you don't want to deal with cavitation and ultrasound, you can of course apply low frequency vibrations, low frequency high amplitude vibrations, and then you can achieve some of the effects similar to what you have with cavitation. For example, you can achieve fragmentation. Yeah, but there's different mechanisms. So it's more, yeah, it's mechanical. It's mechanical fragmentation of weak solid material by inducing some waves there in the melt, and then you kind of, again, by most likely by fatigue mechanism, you will fragment this. There are studies on that. It may work. You can also achieve some effects similar to degassing by introducing vibrations, and that's of course easier because easier depending. For shape casting, it's quite easy. You can just put your mold on the vibro table.
I mean, the big advantage of doing that would not be grain refinement because the steel is processed afterwards anyway. It would be reducing the scale of chemical segregation.
Yeah, that could be, and you also you can have you can reduce probably the effect, the level of macrosegregation by reorganizing the flows, and also you can achieve some degassing, some better mixing of liquid and semi-liquid material. but this is different area of research. So this
Okay.
and I think it's will be quite easy instrumentally to achieve when you have a mold, yeah, so permanent mold, a die, but it's very difficult to achieve if you have continuous processing, because yeah, you need to have
Yeah. Thank you very much.
You will have other problems then.
Okay, but I mean,
yeah.
You know, if there were not problems, you wouldn't have a job. So thank you very much. Okay.
That's very true.
Okay.
Thank you. Yeah.
Any
Yes, Ivan Lorden. I think you are on
muted.
mute.
You muted.
Yeah.
I was just saying that I think Lee was actually first, so if you want to go ahead first, Lee, and I'll jump
Oh,
on
Lee,
afterwards.
okay. Yeah, okay, right. Lee?
Yeah.
Did
I just got probably a quite simple question. You know, this ultrasonic, they got the degassing effect, but in the meantime, it also have the cavitation effect. I just wondering, will this cavitation effect introduce more cavity inside the melt and you know, introduce more gas inside? Can you give more explanation, please?
Yeah. So each of the effects of ultrasound during processing of liquid or solidifying melts has its own temperature ranges where you need to perform it. So when we talk about degassing, we're talking about pure liquid metal, well above liquidus. So we introduce bubbles there. That's true, cavitation bubbles. These bubbles are filled with dissolved hydrogen from aluminium. They grow while they pulsate, and then they float to the surface and release hydrogen into atmosphere. So these bubbles are not creating any extra porosity because they're all present only in the liquid metal, and they will be evacuated from the liquid metal well before solidification starts. On the other hand, you're absolutely right. If you create these bubbles and then immediately solidify, melt, you will have extra porosity. These bubbles will be frozen in, but that's wrong technology. If you talk about technology of degassing, you degas it and perform degassing well above liquidus before melt comes into the mold.
Okay, thank you.
Okay, yeah, please.
Okay. Yeah, first of all, thanks for the talk. I thought it was really interesting, and thank you, Prakash, for organising. So I'd be curious to learn if you've seen any cases of ultrasonic processing used for the solidification of immiscible alloys, and if so, what were the outcomes of those studies at a very high level?
Yeah. So there are works, and there will be works. So I mean, in this book, there is a separate chapter on treating immiscible alloys, mostly like aluminium bismuth, aluminium lead, so mostly model alloys, but with good results. So it's absolutely definite that if you apply ultrasonic processing during when you have these two immiscible liquid metals in the solution, or not a solution, yeah, one is as droplets in the matrix of another liquid metal. So, and then you apply ultrasonic processing at this stage, so the droplets become smaller and more evenly distributed. And then if you quickly solidify it, you will preserve this good distribution. Of course, if you switch on ultrasound and leave it there, it will coalesce again and drop to the bottom. If you talk about bismuth, for example, usually immiscible alloys have light and heavy fractions. So there are examples of that. There was a project in BCAST on immiscible alloys a few years ago when they also added titanium borate, I think, for stabilization of droplets. And it was shown that when you do with cavitation treatment, the result is further enhanced. And we currently try to work in this area. We have one proposal submitted on making miscible alloys and composite materials using ultrasonic cavitation. And I also have some collaboration with international groups in this area on more interest base. Yeah, so I think there is great promise in making such alloys of existing of known systems, but also of potentially interesting other systems to make such alloys. And I think there is a great potential there, because cavitation definitely allows us to have finer droplets and better distribution. I find very promising that we can also combine it with gas saturation and then degassing, because we create more bubbles and they more vigorously vibrate and implode and create more useful effects. Yeah, so this is very promising area. Yeah.
Okay, great. Thank you.
Thank you. Any questions from anyone?
Hello. Yeah, hi. Thanks for the interesting talk. A quick question from me.
Oh, yeah.
Hello. Yeah, whether the viscosity of the metal plays any role in the processing. You mentioned when the cavitation happens and when it implodes, there will be a local rise in temperature. So for degassing, whether we need to account this temperature rise and held the molten metal such that this effect is considered. And for fragmentation, you mentioned that it has to happen below the liquidus temperature. Again, there will be a rise in temperature, but this will be taken into account.
Yeah, if you just saw, so viscosity plays a very important role. So that there are two parameters of liquid metal, which is very important for development of cavitation and acoustic flows: surface tension and viscosity. Density plays a role as well, but yeah. But if you talk about kind of similar alloys or materials of similar density range, so surface tension and viscosity. So surface tension, if you have a low surface tension, so bubbles created very large bubbles, they're very easy to form. And if you have high viscosity, so the process is slowed down. Actually, in glycerin, for example, you can hardly see implosion of bubbles. They are created and they grow very slowly, and the flows are very slow. So everything happens like in a very slow motion. So, of course, it's extreme. Glycerin has very high viscosity. Is extreme case. But if you talk about aluminium and you have aluminium alloys with different viscosities, you add some magnesium or silicon and iron, they change viscosity of the liquid metal. So viscosity affects the dynamics. So if you have lower viscosity, you have better accelerated processes. So if you have great bubbles for degassing, they will rise to the surface quicker. They also will be larger. So if you have low surface tension, they will also become larger and absorb gas more efficiently. So in this, so and if we talk about degassing of aluminium, so this is practically realized in the selection of temperature. So when we want to degas liquid aluminium, we usually select a range between 700 to 740 degrees, where the viscosity is still quite good, because the lower you go to the closer to the liquidus, the viscosity of melt increases and density increases. So the bubbles have more difficulty to float. So you need to have good temperature range where these bubbles can be created and rapidly released. And on the other hand, you don't want to go too high into temperature, because if you go too high into temperature, the absorption of hydrogen from atmosphere becomes more significant. So you degas, but you regas also at the same time. So you want to have a range where you can degas, avoid regassing, but have good kinetics of release of bubbles.
Okay. Thank you. And another quick question. Have you come across this use of ultrasonic waves in controlling the grain size in additive manufacturing? So it's like passing the ultrasonic waves through the mold. So it's like a less efficient process, you would say?
Yeah. So there are a few works up to date where people try to use ultrasonic vibrations to change the structure, so epitaxial growth, let's say, of grains during additive manufacturing, and they typically apply vibrations through the substrate, which is the easiest way to do this. In this sense, I think, and the results are good, but I think that the efficiency of this process is not very high, because you have attenuation, you have a lot of losses when it goes through the substrate, and also you limit it in the height of the build build, because if you vibrate from the bottom, it's very good effects in first 2 layers, but then it attenuates so significantly that upwards you have no effect at all. So this needs to be somehow enhanced, and then you can do this either by direct introduction of ultrasound into the actually build, which is a challenge, because we don't know how to do this. Because in welding, for example, you can put a sonotrod following the pool, So, but in additive manufacturing, the speeds and the cooling rates are so high, so it's almost impossible to do. There are interesting approaches to that by introduction of cavitation through the pulsing laser, and that's maybe a way to do this, because you can induce cavitation by pulsing laser, and it is done in liquids like water. It's one of the means of studying cavitation. You can by pulsing, you can concentrate your energy in a certain point and create cavitation there. Maybe if you can somehow modulate the power of the laser, or introduce another laser which will focus on of melt pool and vibrate, oscillate, the laser power will oscillate in a certain range, so you can create by cavitation there. But the problem is, and that we already had this question, so if you create bubbles, cavitation bubbles, you want them to do the job, you want also them to disappear, you don't want them to remain in the solidified material. So this interaction of velocity of solidification and then cavitation processing itself is very interesting subject, which is not studied yet.
Okay. Thank you.
I think I'm probably next. Thank you very much for your very interesting talk. Can you probably go on mute? Sorry, we're sitting in the same office, that's why. I was just asking, and this is a very naive question. In the very early slides, you showed cavitation speeds of kilometer per second. And if you're looking at this graph, for instance, on slide 11, I was just wondering, actually, how easy is it to distinguish between a very high frequency physical phenomenon that's related to your cavitation and noise that would come from the measurement? Is this at all a problem? Is this very easily distinguishable for metals?
Okay. So 2 things. So when we talk about kilometers per second, we talk about the implosion, the flow which is generated by implosion of a single bubble. So there's a jet emitted, and this happens on the microsecond temporal scale, and on the micron spatial scale. So it's very small small scale and very quick process. When we talk about these measurements, acoustic measurements, we are listening to the overall noise, which is created by everything which is happening in the melt. these bubbles creating, bubbles imploding, bubbles vibrating. They all emit different signatures. So what we do in this case, so we listen to this white noise. Yeah, so we have things like that. Then we process this signal into the frequency domain. So amplitude versus frequency. And then there is usually the fundamental frequency of your main signal. And then there are ultra harmonics, subharmonics, and so on. And subharmonics, they are signatures of cavitation. If you don't have subharmonics, you don't have cavitation. You only have pulsation of bubbles. So, and then on top of this, you can also look at the spectrum in different ranges. And if you talk, so that's we're talking about kilohertz frequency range. If you go to megahertz frequency range, there you can have signatures from the implosions of individual bubbles. And then you can interpret this. It's a direct interpretation of statistical evaluation of what happens in your melt. Yeah.
Mm-hmm. Thank you. Thank you.
Thank you. If no more further questions, it's already 2:07. I thank Dmitry once again on behalf of our group for this wonderful talk. And thank you all for joining. Have a nice afternoon.